Okay, ladies and gentlemen, we're going to go over some extra, we should say motion along a circle examples like I promised you guys. And we're going to continue with what we're doing, rotation of the Earth. And this question number 7, we're looking at the radius of the Earth at the equator measures 3,960 miles. If a person is standing on the equator and the Earth is spinning on its rotational axis at a rate of 1 rev per day, 24 hours, how fast is a person traveling on the equator? In other words, what is the linear speed of a person at the equator in miles per hour? Let me double check to see if we did anything like that. Okay, we're going to go back to number 6, and if you're how far? So number 6, if you guys remember from the lecture, this was how far, right? And so what we did in the past was we looked at arc length. That's the how far part, where S was r theta. And that's distance traveled along this circle here on the equator. So that's kind of what we were finding. You're going around that equator, you're rotating, and they're trying to find the distance you traveled. That's S is r theta. And that's what we went over in class. When we use the angular speed of 1 rev every 24 hours. And the difference between number 6 and number 7 now is number 7 is asking you about rotational speed. They're actually linear speed, okay? So this is a linear speed question. Maybe we paint it blue and we can say linear speed. All right, that means V is r omega. And that's the linear speed of a person on the equator. So if you're standing right here, you're going around the Earth in a circular motion. That's the significance of the radius value. We still have it here in our notes, that the radius is 3,960 miles. That's this value here on the Earth. And you're rotating on the equator. So there's some interesting ideas here. They now want the linear speed. In other words, what is the velocity? What is V? And of course you have the definition of the angular speed divided over time, but we're using the formula that we derived since we already have the angular speed, right? We already have omega, and we have the radius, ladies and gentlemen. So for number 7, you might say, so is it that simple, Mr. Judge? It was designed that way. I wanted you guys to study number 6 before you did number 7. And so my radius value, we know, is 3,960 miles. And then we have that angular speed now, 1 rev every 24 hours, right? So we replace, I think that's the problem. It's 2H. I'm listening to the dog. I hope you guys don't hear that. You guys want a dog again? I can give you one. Anyway, sorry. So how fast is a person moving on the equator? This is what we're going to use. And they want the final answer. And you say in miles per hour, mph. So essentially, you're looking at the answer, essentially, if I write it this way. V is 3,960 miles times 1 rev every 24 hours. And that's essentially the answer. But it's not in the units that they want. They want this in miles per hour, mph. Okay, so this is the desire. And this is really what they want you to do in this question number 7. And so if I copy this, let's try to copy this stuff. Here's copy. And go back to this page here. Sorry. Well, it's saying we are in Keynote. I think we had to go. So yeah, we had to go to this to do our scratch work. If you guys remember, we're now at number 7. So here's our notes for number 7 here. Number 7, we're going to paste this. And let's just do our conversion here. So we're going to have 3,960. Well, actually, yeah, okay, we'll put this down. Miles times 1 rev every 24 hours. So notice the denominator is good already, right? Your units are hours, so we don't have to change the time. What we have to do is convert up here, the revs. And you say, how do you convert revs? Well, remember, we use the unit ratio. We multiply this by the unit ratio of, what did we say? 1 revolution is 2 pi radians. Yeah, there we go. So our revs go away. So we're pretty much set, ladies and gentlemen. And you say, what do you mean we're set? Here's what I mean. You got 3,960 miles, right? Times really 2 pi radians over 24 hours. Remember what I've been saying, that when you see the word radian, that's just code for real number value. It's almost like it's dimensionless. So in some ways, we could just ignore it because it's dimensionless. And so this is 3,960 times 2 pi. We could ignore the radian unit, but we can't ignore the miles unit. And we can't ignore the hours unit. But radians, we can, because that's just a real number. And that's what you got to get used to. And once you do, ladies and gentlemen, notice you're in the desired units. They want this answer in miles per hour. That's what they want this in. So if we give them miles per hour, we're done. We just have to open our TI calculator and, remember the value of pi is 3.14 approximately. But you're going to get a different answer. And then, I'm not in Ecamm Live, so I can't exactly show you with that TI like I've done. So here's what I'm going to need to do here. I'm going to have to find a calculator. Maybe I think I use this one here. Okay. Here's just another calculator I've used in classes. It's a little more cumbersome. This is like an iMac or iPad version, right? And so remember I'm going to put in parentheses, 3,960. And that's times, I believe, 2 pi. Let's see if this calculator understands that, right? And I think I closed this. Let me go back. 3,960 times 2 pi divided by 24. All right, divided by 24. So we're going to divide by 24. And so this is the best we could do this morning, just strictly going with the iPad. And let's just double check. Oh, so here's what they're saying. I mean, if I go out to the nearest tenths, that's 1,036.7. So 1,036.7, ladies and gentlemen. And that's in mph. You got your linear speed. So this is a pretty deep thing, ladies and gentlemen, believe it or not. This is fact, this is reality. That you are actually traveling, if you're standing on the equator, and you go, why the equator, Mr. Judge? Because at the equator, you have a circular motion. And you're spinning at a rate of 1 rev every 24 hours. That's, a day, right? But you're traveling on the equator at a speed, a linear speed around that circle, 1,036.7 miles per hour. Now, you're moving pretty fast. And you say, Mr. Judge, well, then why don't I feel anything? Because that's a constant speed. Remember we talked about that in class? You don't feel any motion if your velocity is constant, meaning the same, doesn't change. You feel it once it changes. If you slow down, you feel it. If you speed up, you feel it. But if it's constant, there's no acceleration and there's no force. And you say, you didn't talk about this. I know. Remember, F equals ma. Constant velocity means your acceleration is 0. You don't feel any force. The force is 0. But anyway, you get to study that in your science courses. But, I get to show you guys some of these ideas. And it's a simple conversion question, really, and your answer's in MPH. So, that's a good question to wake up to. So you said, okay, we did 7. Yep. And let's look at number 8 here now. Okay, so we did 7, and we're looking at 8. It says the orbit of the Earth. Assume that the Earth orbits the sun in a circle with this radius of 93 million miles. That is circular motion. If a year is 365 days, how fast is the Earth traveling in its orbit? That is, what is the linear speed of the Earth, again, in miles per hour? Now, look at the difference between 7 and 8. Because they are very similar. They're analogous. But I'm going to show you now here how they're different. And I guess, okay, I can go to my worksheet. So this is the orbit of Earth. Go back here. And remember, you're standing over here. And you're rotating in a circle with a linear velocity, right, v. And, of course, there's an angular speed there. So you got linear speed, angular speed. And it's connected by the equation v equals r omega. So we're going to use that again. But this time, here's the difference. So you might say, what's the difference? So number 8, we're going to still have a circle. It's a circular motion. So I'm going to draw a circle here, ladies and gentlemen. That's not a circle. Maybe that's more of a circle. And of course, you have a radius value. And the radius is 93 million. And this is that miles. And you are a person. I'm sorry, we're a planet here. There's that blue marble planet we call Earth. And it's rotating the sun in a circular motion. So here's the sun, and the sun probably is a lot bigger. All right, just so you guys know, that's supposed to be the sun, and this is Earth. Now, I'll give you a little fact here. It's a trig course. However, the true rotational, I should say, shape, the orbit of the Earth around the sun. Let's label this. If you guys don't know, and I guess it's an orange sun or yellow sun, the orbit is actually of that of an ellipse, which is a different shape than a circle. So this is a very simplified version of an orbit kind of question. This is not true. We orbit, the Earth orbits the sun in the shape of an ellipse, and the sun is at a foci on an ellipse. You get to study this in more detail in higher math classes, but they give you a very simplified version. And all they're saying is, you know what, that this is going around the circle, and they want to know what's the linear speed, right? That's what they want to know. And v is r omega. So the difference now is this, because you might say, oh, that's nice. They gave me the radius here. And let me get blue. Yes, they told me the radius is 93 million miles. So you might say, oh, Mr. Judge, that's 93 million miles. And then we need omega. We need the angular speed. Now, if I go back to the question, right, number 8, we need the angular speed, and this is what's going to happen. Here's the angular speed, right? What do they want? A year is 365 days. If a year is 365 days, how fast is the Earth traveling in this orbit? And they want the answer in MPH again. All right, ladies and gentlemen, they just gave you here the rate of the angular speed here. Here's what I mean by that. Omega is 1 revolution. Okay. Let's see what happens. Let's see how our Apple Pencil needs to be charged. So to let you guys know, 1 year is 365 days. So if I go back here now to remind you that the angular speed really is 1 revolution every 365 days. Okay, this is different than rotation of the Earth. You're orbiting the sun. So 7 was 1 rev every 2 pi, well, every 24 hours. And that's when you're rotating on the Earth's axis. But this is a orbit around the sun. So there's 1 rev every 365 days. So that's the difference. So in number 8, we say 1 rev every 365 days. And that could because that's our omega. So now you have the V equals, if we focus on that, here's my R radius, and then here's my omega. So as you guys remember, this really becomes conversion, meaning V is 93 million miles times 1 rev every 365 days. Now remember, we have to convert our revs. There's 1 rev every 2 pi radians, or real number value. So the revs go away. That's one thing. And then remember this, okay? Because my units are now going to be essentially miles per day, because radians is just a real number. So I can even just forget about it. They want our answer in mph, and that's in miles per hour. So I have to multiply another unit ratio. We have to relate days to hours. See this days down here? We want it to cancel with days. So what's the relationship between days and hours? I think there's, for every 1 day, there is 24 hours. So you cancel the days and you're left with just hours. So this is in miles per hour now. So take a good look at that, ladies and gentlemen, because this is essentially what you really have to do. It's not that bad. So we got 93 million times 2 pi over 365 times 24. So just go back, if you will, and determine what's left, right? Maybe I'll change the color. 93 million's left, 2 pi's left, and that's on top. 365 and 24 is on the bottom. So we're writing this down, and then the units are going to be in miles per hour. mph. Don't forget the value of pi is approximately 3.14. So this is what we're going to enter in our calculator. Right, give you guys some time to take notes on that one. Okay. Alrighty. Okay, so let's go to the calculator. 93 million, 2 pi, 364, 24. So I think there should be a nice clear function here, but I can't see it. 93, 1, 2, 3, 4, 5, 6. And I forgot to put parentheses. So parentheses, 93. 1, 2, 3, 4, 5, 6 times 2 times pi. Oops. Divided by, let's close that. Divided by, what was in the denominator? Do you guys remember? 24, I think. 365 times 24. Okay. 365 times that 24. Close that. Let's make sure we have 6 zeros. 1, 2, 3, 4, 5, 6. Okay, it looks good, ladies and gentlemen. You think it's okay? Look at this. This is the speed in which we're moving. The Earth is orbiting the sun. Not really in a circle, but an ellipse. But for this question, let's go out to the nearest. If we go to the nearest tenths, it's still 66,705. So my linear speed $66,705 miles per hour. We abbreviate that mph. So there's the nice gory details. All right, just looking at this here. And then I'm going to say, if we look further at this worksheet, you're going to have some area questions. I kind of think you can't answer some of these at this moment. So I'm going to say for these 9 and 10 on your homework, I'm going to say stay tuned. You will at the end of the week. So there's more, I should say, sections we have to talk about to answer 9 and 10. So stay tuned. At the end of the week, we can do that one. Stay tuned. And what I think I want to do is go through some questions I see in the book that are going to be very helpful. I'm going to go over some questions, but I got to change them because there's copyright issues. And we don't want to violate copyright laws. Okay? So I'm going to change some. You'll probably know what I'm talking about if you guys are up to date and taking a look at some of these things. And I know you are. So I'm going to go through what we call a latitude question. Latitude. Okay, so this is leaving that worksheet that I gave you guys. Stay tuned. You can do the rest in the future. We'll talk about that because there's more material to cover. And we're talking about a latitude question, and you have to know, and I think there's one T in latitude, so let's get rid of that. So we got a latitude question. And I guess to remark about latitude, if I look online here for latitude, maybe I do have a browser. Show you guys something like this. We're talking longitude and latitude. This is specifically latitude. So if I look at, one of these kind of questions, I'm not sure. I think this is kind of a good one here to look at. Maybe you get that picture. These are the lines that run across a map from east to west. The point latitude makes the nth. Okay, you get some definitions here. So let's take a look here. This is kind of the picture I want you guys to see, right? Here's latitude. And so here's a globe. There's the equator. And I don't think I can write on this, but if I say add to photos, okay, let me do that. I added to photos. I'm going to try to bring this in. So, bring this one in. What I want to show you here is with the latitude, you got latitude and longitude. So latitude, is really the measure of distance north or south of the equator. All right, let me say that again. The latitude is defined to be, it's a measurement of distance north or south of the equator. So you have this equator here, and you have these lines here that represent this latitude. And then you have something called longitude, but we're not looking at latitude. So you have these kind of lines, if you guys can see that here. And the kind of questions they ask you, like in your book, I'm gonna write it this way. You have these things called a meridian. You say, what's a meridian? We should talk about that. Meridian, it's we have various definitions again from geometry. A meridian it's a circle that consists of a longitude passing through a given place on the Earth's surface and its terrestrial poles. So you got these meridian values, and I'm going to draw a picture here. Here's kind of what they're saying. These are kind of the meridians, and you have something called the prime meridian, but they're the meridians. And so they're kind of like these vertical lines that go across the globe. And so a typical example could be something like this. And it's going to be measured in, degrees, but we can say city A is located at 40 degrees north in latitude. And then we're going to say the following. Something like this. City B is located at 50 degrees north latitude. And they're going to make this point clear. Along the same meridian. Okay? So let me go back and show you here how we can look at this picture. Here's a meridian. Maybe we share that in red. Let's be very cognizant of the colors. And so here's this particular meridian, if you will. And then they say city A has a location 40 degrees north in latitude. Now, if it's north, it's above the equator. So I want to say to you, being north is above the equator. That's what being north is. South is below. So if you can see, this looks like this is a line, and this is 30, and then another line here, 60. So 40 degrees is a little bit above. So it's almost like saying, here's city A, and then you're going to 50 degrees, and maybe here's city B. And it's like on the same meridian, but this is the latitude values. This is the degrees north of the equator. This is how they have it written here for you. Okay, and they're like these lines here, by the way. They're the horizontal lines. These are the latitude lines. So you have a meridian, which is vertical, and the other lines are measuring your latitude. If they're above the equator, that's north. And if they're below the equator, that's south. And so here's the big question. This is what they want you to ask, really. How far apart is city A from city B? And what they're saying now, if I make this a bit bigger, is they want to know this distance. And it's the distance on the globe. So they want that distance. And you go, how am I supposed to find the distance along an arc? Because city A and city B, they're on different latitude locations, but along the same meridian, meaning the same vertical line, which is your meridian, and then these different horizontalish lines on a globe, which is your latitudes. And being above the equator, they're both north. So, if they say south, well, it's below the equator, and it works the same way. Anyway, they're asking a linear distance on a circle? Let me say that again. How far apart? They want what? How far? That's distance. Ladies and gentlemen, they want to find how far? That's distance. Okay. Let me remind you guys something here. You have a way to measure distance along a circle. It's called arc length. So you might say, do I use my arc length formula? And I'll say, yes, you do. So this is really an arc length formula question, ladies and gentlemen. S is r theta. You say, what do you mean? Well, let me kind of draw a picture for you. Let me cut this globe. If I go back to the globe, I'm going to cut it along the meridian. You go, what does that mean? I'm going to cut it along this sort of, and that's behind it. And what you'll see is a circle. And here's kind of how this works here. And let's try to draw a circle. All right, come on. So here's my circle, and I'm going to say this portion here is the equator. And you say, does that mean that this portion here is the radius? Yes, it is. Of the Earth. So that's our Earth. And then let's talk about this other portion. You say, but how do they find these latitude measurements, right? How do they say 40 degrees north and 50 degrees north? Here's what that means. Where they get this, ladies and gentlemen, is this picture of the circle. Meaning, here's where city, was that A or B? City A is 40 degrees north. So here's where city A is on the surface of the Earth, and that measures 40 degrees, ladies and gentlemen. And then I'm going to change the color. Let's do a dark green. And here's where city B is. And city B, right in here, measures 50 degrees. So you guys see that. And that's kind of what's happening here. And so if you said to me, but you just said I use the arc length formula. Yes, we do. Because the distance, ladies and gentlemen, from A to B is along the circle here. That's on the surface of the Earth. This is S. So you might say, I have a sector. Yes, you do. This is a sector. And then I'll say to you, how do you find arc length of a sector? You'll tell me, oh, I know. And I'm going to try to, I know I'm drawing it horrible. You need a radius, you need a radius, you need a central angle. That's going to give me my arc length. And so you are really looking for that. But in this case, ladies and gentlemen, we have to find theta. And theta is this angle right in here, whatever that measures. And you might say, if the green angle, if this whole thing is 50, and the blue angle is 10, isn't the central angle here going? I'm sorry, I gave you the answer. 50 minus 40. If the green angle is 50 and the blue angle is 40, that central angle for our sector is 10 degrees. There you go, ladies and gentlemen. So here's what we really want to look at. $10 degrees, radius of the Earth. That's just our R value. We have to remember what that radius was. Without it, we can't answer this question. So we have to go back. Where was our radius of our Earth? Oh, 3,900. This is number 7, right? Here's our radius of our Earth, 3,960 miles. So the distance on the surface, 3,960 miles, you might say, I can find the distance between city A and city B. Okay, so this is how we handle, distance along a meridian. And you might have to remember, you say, okay, I remember my arc length formula. S is R theta, but you say, Mr. Judge, your theta has to be in radians. And I'll say, yes, it does. You're going to convert. So S will be 3,960 miles times, you might say times 10 degrees. Yes, but convert degrees to radians. So we say, is there 180 degrees for every radian? And I'll say yes. And that'll make your degrees cancel. So you'll have your arc length going to be 3,960 miles times 10 over 180. So, you can move your miles at the units at the end. You could put your numbers together. Times 10, you could say that's in miles. And now that makes sense. So if we go to the calculator, I think we had 3,960 times 10 divided by 180, which is 220. So take a good look at that, ladies and gentlemen. 3,960 times 10 divided by 180. Let's double check. Are we okay with that? 3,960 times 10 divided by 180. 220. Okay. So the distance on the Earth, ladies and gentlemen, the arc length, 220 miles. So these cities are 220 miles away from one another. $220. And that's kind of an important thing, ladies and gentlemen. This is the surface of the Earth here, and this is how you compute distance along an arc, along a circle. Okay, it's not a straight line. It feels like a straight line. If you said, I just went to San Diego, 220 miles away, you know what kind of distance that was, really? That was an arc length. It is linear distance, but it's an arc. It's a distance along a circle. Distance traveled. So that's how we handle these kind of situations. And then I'm going to give you another city and say, by the way, and I'll say, note. What about city C, which is located at maybe 25 degrees south along the same meridian? What's the distance between city A and city C? Okay. So you might say, okay, do I have to draw a picture of a globe? And I'll say, no. Here's what you guys can do. We're going to copy this picture here. And I'm going to erase this our Earth and say city C now. Let's change the color. Orange, 25 degrees south of the equator. So I'm going to do this. This measures 25 degrees. And that's where city C is at, because anything that is south, they mean put it below the equator. Anything north is above. And then now, if you will, you might say, what do they want now? So maybe I should copy it, city A and city C. So let's copy it then. Look at this at the bottom. I'm going to get rid of this in green. So I'll remind myself, and then I have another angle out here. Yeah. And so I want you guys to notice this. I might have to make my eraser extra small. All right. This is the arc length. That's the distance on the surface of the Earth. So remember, you're cutting the Earth along a meridian. You create a circle. The radius of the Earth is 3,960 miles. That's where the equator is. So anything north is above the equator. Anything south is below. However, if you said, okay, but Mr. Judge, I see that we do have a sector in red, but the central angle of my sector now is different. And I'll say, I know it's different. Now, the central angle, 40 plus 25, 65 degrees. And the radius of the Earth is 3,960 miles. This is the arc length. So S equals R theta, means 3,960 miles times 65 degrees. And you guys know we got to convert that to radians, because in our definition, it's radian measure. You say, well, what's the conversion here? Well, remember that it's 180 degrees, 2 pi radians. So we can find the distance on the Earth this way, 3,960 times 65, your degrees cancel, times 2 pi. That's going to be now in miles. And you say, is this in, radian miles? I'll say, no, radian means a real number. So it's just in miles. And double check, make sure 2 pi radians, 180 degrees. Yeah, it looks good. So we're going to have to remember, 3960, 65 times 2 pi. Let's try this out. 3960 times 65 times 2 pi. Something's bothering me here. We made a mistake. It's not a million miles away. What's the issue? There's the issue. Where do we get the 2 pi from? Let me go back to the last example. We made a mistake. Let's go back. Two pi radians I have to have the right ratio. Here's our mistake. It's not 2 pi. It's pi radians per 180 degree. Sorry about that. That means we made a mistake in the prior one, and we're going to fix it. So 3960, 65 times pi over 180. It's 4,492 miles. We're going to go out to the whole miles. 4,492 miles. So we're going to fix it because we made a mistake. Apologize there. Remember, if I catch it, it's not a mistake. Here's our mistake. We got to use the right conversion. Pi radians to 180 degrees. I'm going back here. Here's a mistake, ladies and gentlemen. Oh, I have it. It's not, no. It's right here. We forgot the pi. Pi radians. It's 180 degrees, so there's a pi here. So let's fix that one. Okay? This one is 4,492 miles. Don't forget your proper conversion. Now let's fix this one. 3960 times 10 pi over 180. Alrighty. 3960 times 10 pi over 180. $691 miles to the whole mile. So let's double check. 3,960 times 10 pi divided by 180, 691. Let's fix that one. I apologize. Anyway. We should probably draw a nice 91. Okay, ladies and gentlemen, here is how we find distances along the sort of surface of the Earth. Remember, we're on a globe here on the surface, so it's not a straight line. It's actually an arc. So maybe I'll stop right here. This would be good for you guys to answer some of these questions on your homework for the applications. And some of the area questions we're going to have to get back to at the end of the week. So anyway, ladies and gentlemen, here's a video I promised you guys. Take a look at it. It has some good stuff. We did catch our mistakes. Yes, caught it myself, even though I had 2 cups of coffee and I slept in. Still, as you guys know, you old men make mistakes. So take a look at it and see how you guys feel about it. And you have a great weekend. And I'll upload this as soon as possible.